Hello students, welcome to TSS Tutorial Center, where we make complicated topics very simple to understand. So if you are under natural and applied sciences and you want to become good, you want to become better, you want to start thinking outside the box, then do subscribe to this channel, because we break down complicated topics to something which you're going to understand in just a short period of time. Fima Zwibo! Zwibo dude. In this tutorial, we talk about vibration and waves, and it's something that you already have some ideas about. Before you watch this video, make sure you watch deformation of solids. That's the first video you're supposed to watch. Okay, so let's start. What are we supposed to talk about? Vibration and waves. We'll begin with Hooke's law. In Hooke's law, we've been talking about it, and most of the people, you know what it states. What is Hooke's law? We said when you have a spring, then you apply a force at the far end here. What's going to happen? According to what we said the more force you're going to apply, the more force, then the more the extension, or the more the spring is going to extend. So this force in the extension, which is here, we said they are directly proportional. And we said when we remove the proportionality, we're going to have a constant which is known as the spring constant. And we said the spring constant, it has units, and that is Newton per meter. When you make this the subject, the spring constant, the subject, you're going to have force as the numerator, and the extension has the denominator. So the spring constant, the units are Newton per meter, and it tells us the stiffness of the spring or the material that we're talking about. Okay, so this force that we are applying to stretch or compress the spring that we have is known as the force applied. Now, the spring is also going to apply a force on its own, trying to get back to its original position. Since it's elastic, it will be applying a force in the opposite direction to the applied force. That force will be resisting the motion. It will try to get back to where it was. So this force the spring applies is known as the restoring force. The restoring force, Fs, the restoring force. Okay, so what is the restoring force? This is the force the spring applies in order to get back to its original position. Okay, so at this point, the displacement was x is equal to 0. Now when we start extending, the extension is going to be changing. The extension is just the same as displacement in this case. So it will be changing. It can be 2, it can be n number. When it reaches the maximum extension, which is denoted as A. It's denoted as A because it's known as the amplitude. This is the maximum displacement the spring undergoes when it is stretched or compressed. Okay, now let's move on. What else are we supposed to talk about? We have talked about two forces, this one and this one. The question is, what is the formula for the restoring force, Fs? Okay, so since this guy is trying to oppose the motion, it's going to be the same formula but negative. Here still we're going to put the extension. The reason why it is negative is because it is opposing the motion, and as we were applying the force, the displacement was in this direction, and the force is in the opposite direction. That's why it is negative. So far so good. Okay, so when talking about the acceleration the spring is going to undergo, how is it going to be? To come up with a formula is very simple. We use the restoring force, and we said it's given by negative spring constant and times kx. Okay, what else? We also use the second law of motion, Newton's second law of motion, which is F is equal to what? ma. This is from grade 12, so I bet you know about this one. And since this one is force and this one is force, we can equate these two so that we have ma is equal to negative kx. What are we going to do? We want to make a the subject, so we'll divide by m and we'll remain with this expression. So this is the formula we're going to be using to calculate the acceleration in a spring. Now take note, we said the maximum amplitude when we stretch is denoted as a. This is the maximum, which means the minimum is going to be negative a. So in this case, the acceleration at this point is going to be what? We're going to substitute the value of a. So think of a as n number. It will be m. What about on the minimum? It's going to be e. Negative and negative, they are going to multiply, so you have this. Okay, so this totally means that the acceleration we're going to have is just going to be ranging in this range. It will be from this one to this one. This is the range. This will be the maximum acceleration. This will be the minimum acceleration. So the acceleration is maximum at the maximum amplitude. So far so good. We move on. From there, we're supposed to know the energies that are going to be there whenever we stretch a spring. So suppose we stretch, we apply a force. This is where x is equal to 0, then it stretches. At this maximum point, there's going to be energy which is going to be stored. That energy will be the one which will be trying to be converted to kinetic energy so that the spring gets back to its original, or where x is equal to 0. Now look at this. We're saying at this point there is elastic potential energy. At this point, elastic potential energy, which is denoted as this. Now, when you remove your hand from this point, you release the spring. What's going to happen is this energy is going to be converted to kinetic energy, and the spring will start to do what? Moving. It will move in this direction. So moving in that direction, it will surpass x is equal to 0. And it will move to where x is equal to negative a. The minimum amplitude, again at this point, it will store potential energy, elastic potential energy. Now there is nothing which is holding it, so that elastic potential energy again will be converted to kinetic energy, and again it will cause the spring to move to this point. It won't reach a that much, but it will be a little bit there. It will be a little bit where a is. Again at that point, it will be converted to what? The elastic potential energy that will be stored will be converted to kinetic energy again until it reaches where x is equal to what? 0. So it will be like moving, boom, 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 boom. Okay, now let's talk about where x is equal to 0. We say that this energy will be converted, slowly be converted to kinetic energy, slowly be converted to kinetic energy. When it reaches E, this potential energy will be entirely converted to what? Kinetic energy at x is equal to 0. So at x is equal to 0, kinetic energy is the maximum. Now since kinetic energy is the maximum, this means even velocity is going to be the what? Is going to be maximum. Okay, so at x is equal to 0, v is the maximum. Okay, so those are the things you're supposed to know. I'm sure you might be asking yourself the question to say, what formula am I going to be using to calculate the elastic potential energy? It's actually simple. It's given by 1 over half, 1 over 2, k a squared. This is only when it's at the maximum. But in general, just put x here. Okay, what else? According to the orientation of the spring, it can also store gravitational potential energy. We'll come and talk about this. But we already know that the gravitational potential energy is given by what? mgh. According to the conservation of energy, let's say this is the initial point. We stretch to reaches at point A. The energy which is going to be here is going to be the same throughout the spring, but it will be transformed into different types of energy. That is, at this point, there is elastic potential energy, there is gravitational potential energy, there is also kinetic energy. We are going to call this as the initial, the starting point. Then the final point is going to be these energies, and some are going to be equal to 0. Then kinetic energy will be there. Okay, so we say that according to the conservation of energy, energy is not destroyed nor created. That's why we're saying the initial is just going to be the same as the final. The monaka promoter. The initial is just going to be equal to the final because energy can never be destroyed nor created, but it can be lost through friction. Imagine at this starting point you had 200 joules of energy. Then you ended up with 150 as the final energy. There is energy which is missing from this guy. That is 50. So 50 is the energy which is lost through friction. Now how do we calculate that? So what we do is we just subtract 150 minus 200, and it's supposed to give us negative. So it will be the initial energy energies, that is these energies that we have here, minus the final energy. in this case, what we're talking about is 150 minus 200. It's going to give us negative 50 joule. That is the energy which is lost through friction. Okay. And lastly, you're supposed to know how to come up with this formula. This formula is very important, and one should know how to come up with it. Okay, so according to what we were saying when we stretch the spring and it reaches at this point, bubble, it's going to store energy, not so. That energy is what? Elastic potential energy. So at this point, just going to store the elastic potential energy, the total energy. And we said it's given by this formula. Since it's at the maximum, we're going to put A here, raised to the power 2. Now what are we going to do? Imagine the spring is released, then it reaches a point, end point, let's say X, from where it was, it reaches a point X. Then at this point, since we were saying this energy is slowly converted to what? Kinetic energy. So definitely at this point is going to be possession of kinetic energy and potential energy at this point. So the total energy is going to be equal to what? It will be equal to the kinetic energy plus the elastic potential energy, which is going to be at this specific point. Now we know that the formula for the total energy is this one here. So I substituted where I'm seeing the total energy, I'm substituting this. And the kinetic energy, that one we can't forget, it's from grade 12 and we've been using it a lot of time. What about this point? What is the elastic potential energy? It's going to be 1 over 2. Then K X raised to the power 2, since it's not at the amplitude. Okay, then what we're going to do is we're going to multiply this equation by 2, so that we have K so when we multiply by 2, this one and this one, 2 divided by 2, 1 multiplied by this, everything will be just 1, 1, 1. Okay, then from there we're making V the subject. So what we'll do is this guy will cross the cosine. Let's factorize K, so that we have then from there let's divide by V. Then finally we have come up with the formula. And this formula shows us that when X is equal to A, velocity is going to be 0, because you're going to get A, you substitute here. So it will be A squared minus A squared, which is 0 times everything that you have, it will be 0. So at the maximum point, at this point where it's not moving, V is equal to what? 0. However, when X is equal to 0, what is the value of V? We said it's the maximum. When you substitute 0 in this expression, you are not subtracting anything from this guy, so it will be still at its maximum. So this one will be the maximum, even velocity is going to be the maximum. Okay, let's do some questions about the same thing. So this is the question that we have. Question is saying A 1,300 Newtons car starts from rest and rolls down a hill from a height of 10 meters. It then moves across a level surface and collides with a light spring-loaded guard rail, negating the friction and ignoring the rotation kinetic energy of the wheels. Find the maximum displacement or the distance the spring is compressed. Assume K is equal to this. Okay, so what are we going to do here? Let's try to draw this scenario. Suppose this is the hill they are talking about. Then there is a spring at this point. This is 10 meters. And the car is here. To solve this question, what is the distance? We're going to use what we talked about, the conservation of energy. That is, the initial energy is equal to the, is equal to the what? The final energy. And there is no energy lost through friction, according to the question. Okay, so they're just saying that the initial energy is equal to the final energy. And according to what we said the initial energy that is going to be the elastic, is going to be the gravitational energy, and the kinetic energy. From here, you know that there will be a point where the energy is just zero. We're going to remove it from the question. The same thing is going to be here. The only difference is going to be, this is going to be the final. Okay, so this is going to be the final. Okay, so looking at this point, what energy do you think the car is possessing at this point? Quite alright, it is not moving because they say it from rest. So what energy is going to be omitted from here if it's not moving? Kinetic energy, because that is energy in motion. Now, do we have any spring here? No, we don't have. This is known as the elastic potential energy, and it's just for the spring. So we don't have the spring at this point. So the initial energy that we have is just the gravitational potential energy. What about the final? It comes here, then stretches the sky at a certain point, and it's going to be the maximum. What do you think is the energy which is going to be there? When it comes at this point, it will stop moving, boom, then it will be thrown back in this direction. Now we want at that point where it is not moving, so the kinetic energy is going to be cancelled as well. Gravitational potential energy, it is no longer above the ground, so gravitational potential energy is not going to be there as well. So this is the formula we're going to use, this guy and this one. Potential energy and gravitational potential energy. Gravitational potential energy and the elastic potential energy. Now, we know that gravitational potential energy is given by this, and the elastic potential energy is given by this. We're looking for the value of x. What are we going to do? Cross multiply to come this side. What else? We are going to divide by k. Dividing by k, this is what we're going to have. And making x the subject, so it will be the root of 2mgh over k. can substitute the information that you have. Two. Now we don't have mass, but we've been given the force, and we know that mg is the force. So I'm going to substitute 1,300 at this point. What about the height? The height is 10. What about the value of k? This one here, 1.0 times 10 raised to the power 5. Punch this on the calculator, you are done. Okay, so you should get 0.5099. This is going to be in what? Meters. Okay, what about the next question? Calculate the magnitude of the car's maximum acceleration after contact. Okay, so as we said, this is the formula we're going to be using. We're just finding the magnitude. Magnitude is always positive, so you can ignore the negative. Squared. Okay, so you're just going to get the value of k. And this raised to the power 5. And this is m, which means you're supposed to find mass. And this is what we found from question A. So if you got this one wrong, even this one will be wrong. The acceleration is going to be wrong. So be careful. Now in this case, we don't have the mass. We're supposed to find the mass. That's going to be simple. Okay, so we know that the force that we have is and the mass, that's what we're looking for. Gravity will divide this by 9.8. So we can have the mass as 132.6. So where we're seeing mass, we substitute 132.6. And finally, you're going to get the acceleration. So you can do that. This is very simple. Lastly, a 0.5 kg object connected to a light spring with a spring constant of 20 Newton per meter accelerates on a frictionless horizontal surface. Calculate the total energy of the system and the maximum speed of the object if the amplitude is 0.03 meters. Okay, even this question is very simple. Think about it. They're talking about the maximum, the total energy, and we've been given the amplitude. So the total energy, as we said, is going to be given by, instead of putting x here, it's going to be a, because that is the amplitude, the maximum amplitude. And we're going to substitute your data. So here we'll have 20, then the amplitude 0.03 raised to the power 2. Then you punch this on your calculator. That is the maximum energy. So you should get 0.009. Then from there, what do? Just put the units. Okay, so Again, the question is asking us to find the maximum speed. Remember, we said the maximum speed is at x is equal to what? 0. And velocity, as we talked about, is given by this expression. And we know that x is equal to 0. So just substitute the 2's again. This is 20. What about the mass? 0.5 multiplied by the amplitude. This is 0. What are we going to